Hello, welcome to our next unit of mathematical reasoning. We're covering section 7a, so we're getting into probability, our third unit. So we're going to start off with the basics, the fundamentals of probability, get an overview of what probability is, so that we can move on and talk about all different ways to calculate probabilities, look at some of the repercussions, some of the things that we get from probabilities, understanding them, things we can not get suckered by. There's a lot of real life is trying to sucker you into, paying money and stuff with probabilities, and so you can avoid some of those things if you understand probability a little bit, which is our goal here. Now, the first most basic thing you need to understand about probability is the most basic possible result of an observation experiment, which is called an outcome. So when you flip a coin, you roll a die, when you draw a card from a deck, when you buy a lottery ticket, anything like that, the outcomes are all the different possible results you could have. So all the different cards that could come out of the deck, all the different sides of the die could land on, heads and tails on a coin are kind of basic. If you toss multiple coins, like toss 2 coins, the combination heads and tails would be one outcome if you were tossing 2 coins is what you're doing. So this is the most basic possible result of an observation experiment. You can't flip 2 coins and just get 1 heads. You have to get 2 things. You're flipping 2 coins. So that's why the most basic option for flipping 2 coins would be something like heads and tails. Or you could get tails and heads, or heads and heads, tails and tails. So those would be the outcomes. Now, when we do probabilities, we're typically actually looking at events. An event is a set of outcomes that share a property that we're interested in. So usually I don't look at every single individual one and say, I'm going to find the probability of all those. I say, I want to find the probability of a certain situation, like maybe getting exactly 1 head. So I'm going to flip 2 coins, looking what are the chances one of them is going to come up head. I don't care if it's the first one or the second one, but one of them comes up head. And so those things all share the property of having 1 head. So they share a property. It's outcomes that share a property that we're looking at. So example, keep on going with this idea of flipping 2 coins. So if we're tossing 2 coins at the same time, we can see that there's 4 possible outcomes. The 4 possible outcomes is you could get no heads, you get tails, tails. You could get tails, heads. So you got 1 heads. You got heads, tails, and you got heads, heads. Those would be our 4 possible outcomes. And then they fall into these different events. If we're looking at the number of heads, the events would be, no heads. So we got 2 tails, there's no heads. You're getting 1 head, which getting tails, heads, or heads, tails, they're both the same event, which is getting just 1 heads. And then the event of getting 2 heads, where they get both heads. So even though these are 2 different outcomes, they would fall in the same event category. And it is possible for an event just to have 1 option, right? Trying to get 2 heads, there's only 1 option if you're flipping 2 coins where you get heads. So there's only 1 outcome that falls into that event of both heads. So it's okay, sometimes events have only 1 option, sometimes they have multiple options. Event, though, is everything that shares the same property. Notice that we do count the outcomes tails, heads, and heads, tails as separate because they are, yes, the same 2 coins, 1 tails, 1 heads, but we can get that 2 different ways. The first one could be the tails, the second heads, or the first one could be the heads, the second one tails. So those are 2 different ways to get that outcome. I can't get heads, heads a different way because the first one has to be heads, and the second one has to be heads. I can't change it and make it anything else and still get heads, heads. So there's only 1 option that gives me heads, even though I need both coins to come up heads, versus where the middle terms where I have 2 different ways to get a heads and a tails. So let's look further at another example. So we have a dog. It's going to have litter of puppies, just 2, not a big litter, just because we want to keep it simple. And they could be black, brown, or white puppies. They can have a combination way. We want to list all the possible outcomes for 2 litters. So we're going to have our first pup, and we're going to have our second pup, and we're going to think about the possibilities. Well, the first pup could have a black puppy, right? And so could the second pup. So it could have the same black puppy. Well, not the same, another black puppy. But there's more options, right? Because the first pup could be black, but the second one could be brown. First one could be black, but the second one could be white. And those would all be options. Each one of these is a different outcome. Black and black, black and brown, black and white. Of course, the first puppy can be a different color. It could be brown. We could have a brown puppy and a black puppy. We could have a brown puppy and a brown puppy. 2 browns. We have a brown puppy and a white puppy. Those will all be options. And of course, the first puppy could be white as well. So we have white and black, white and brown, and white and white. And that would give us all the different options, right? So we have 3 different options for the first puppy, black, brown, or white, and the second puppy could be black, brown, or white as well. 3 different options for that one as well. So we actually end up outcomes. So even though they're only having 2 puppies, with all the 3 different color options, it ends up being like 9 different possible combinations, 9 different outcomes that could happen. Now, if they're looking specifically at the number of white puppies, maybe they're excited to have a white puppy, or maybe they don't want the white puppy, but as soon as they're looking at white puppies, our events, we would think about the number of white puppies. So I think about like the first option here, no white puppies. That would be one of the options, as there's no white. That would be an event. And there's lots of outcomes that fall in that. Black, brown, or black, 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 brown, brown, black, brown, brown. And those would all be options that would be no white. You could have both white. Instead of having none of them white, you can have both of them be white. There's actually only one option that works for this, and that'd be the option down here, right? White, white. That's the only one where they're both white. The rest, they have one of them white, or none of them white, but this is the only option with both white, is white, white. And then the last option is you could have one white. So instead of having both white or one white, or no white, we have one white. And so like the black, white, white, black, white, brown, there's about 4 options that would be one white. And these would be the events. So typically I don't say what's the probability of like getting exactly a black or brown puppy. Usually I want to know what's the probability of getting, no white. And that would be giving me a black and brown, or black, black. Or maybe I want the probability of getting at least one brown and one black, or getting one brown and one black. But that could include black, brown, or brown, black. Those are both the options where you get one of each of those colors. But a lot of times we'll just say, okay, I don't, what's probably I don't get any white. It's probably get both of them white. It's probably one white. Or you could do the same thing with brown, or the same thing with black. So events, again, they're clusters. Sometimes only one thing fits in that category. There's only one outcome that fits that event. But most of the time, there's going to be multiple things. A big part of finding probability is figuring out how many outcomes, fit in that event, and also figuring out how many different outcomes we have for this probability, for this thing we're calculating. And that's what we're going to be working on most of the time, is figure out these numbers of options, the number of outcomes, and for events and for the total. Now, when we find probabilities, it's good to know a couple basic things about probabilities. First off, the way we're going to write it. We don't want to sit here and write probability over a decently long word, and especially when we have to say probability of event blah. A we'll use as stand-in for whatever event. It could be white puppies, it could be brown puppies, it could be something like that. We'll be finding the probability of some event like that, and just to make it shorter, so we have to sit there and write that whole thing, probability of A, over and over and over again. We're going to use this notation where it says P of A. So P of A, that just means probability. We'll just use P instead of the whole word probability. Who wants to write the word, we can just write P, and people know what you're talking about. And then we just put parentheses, and we put A inside. We're not multiplying. I always get people to think that you're trying to take P times A because they're used to doing that with parentheses. No, this is just a notation saying find the probability of A. Find the probability of the thing inside here. And so A will get replaced. Later when we're rolling dice, A might be rolling a 5. Or if you're flipping coins, A might be getting heads. If you're drawing cards from a deck, A might be getting an ace. So A is going to be the event. That's what we're going to put in there. And you'll see me do that. Well, I write P of, and I'll put something inside parentheses. And that's the thing we're looking for. Okay, so probabilities. Probabilities are always going to be between 0 and 1. It is impossible to get a negative probability. You cannot have a negative chance of getting something. You can't have a negative chance of winning the lottery, or a negative chance of winning at cards. You can have no chance, and that would be 0. But you cannot have a negative chance. So probability is always going to be bigger than 0. They're never going to be less than 0. Also, you can't have more than 1. Now, what about like 100? Well, usually when you think about 100, when you think of probability, you're actually thinking about 100%. Because 100% is actually the same thing as 1. 100% is 1 if you turn it into decimal form. So if you have a 100% chance of getting something, it means it's guaranteed. You can't do better than that. You can't do better than guaranteed. I can't say, okay, I'm going to win this game. I'm 150% probability that I'm going to win it. No, it could be up to 100% probability. I can be sure I'm going to win, but it can't be more than sure I'm going to win. You know, people might say that on TV or something, but that's not real. You can't actually have more than 100% chance of something. The 100% is the highest chance. That's the same as 1. So every probability is between 0 and 1, which you'll notice, you know, that means we're going to be dealing with like small like fractions. You can write them as percents, decimals, fractions. I'm really not too worried about which method you use. Most of the time I'll write mine as fractions. We'll see as we go further on that it just makes sense a lot of times to use fractions. But yeah, these can be percents, they can be decimals. All of those are valid ways to write your probabilities. So probabilities are always between 0 and 1, and they can include 0 and 1. And so the chart kind of shows here, 0 is on the impossible end. If you have a 0% chance of winning the game, you're not going to win. That's what that means. It's impossible. It's not going to happen. Anything less than 50-50 chance, we're going to call unlikely. So this is anything from I have like a 0.0001% chance all the way up to I have like a 0.45% chance. As long as it's less than 50% chance, you know, as long as it's less than half, then you're unlikely to win. You're more likely to lose than you are to win. Anything below 50%, that's what that means. 50-50 chance or 50% chance, 1/2 chance. This is all saying that you're just as likely to win as you are to lose. You know, those are equally likely. So this is when you flip a coin, and it can come out heads or tails. If you win on heads, well, then you have a 50-50 chance, because there's, you know, half the time it's going to come heads, half the time it's going to come up tails. So it's 50-50 chance. Anything above 50-50 chance is considered likely. These are probably going to happen. So this is likely. Anything above 50-50 chance, you're probably going to win. That's what that's telling us. So even if you have like a 55% chance, that's not very much more than 50% chance. That still means you're more likely to win than you are to lose. Same thing if you got a 95% chance. You're almost always going to win. Like 19 out of 20 times you're going to win if you have a 95% chance. So anything above 50%, you're more likely to win than you are to lose. And then, of course, 1, that's 100%. That is certain. So if you have a 100% chance of winning, you are going to win. Like, you know you're going to win. It doesn't matter what happens, you're going to win. That's a 100% chance. So the smaller the probability, the less likely the event's going to occur. The larger the probability, the more likely. Again, 50% or 0.5 chance means equal on both sides, like flipping a two-sided coin. Okay, so let's just kind of practice our idea of this idea of having impossible to certain, what that means. So we're going to consider some probabilities, and we're going to state if they're impossible, unlikely, 50-50, likely, or certain. So drawing an ace of spades from a deck of cards. Well, there is an ace of spades in the deck, right? But there's only one. You know, typically decks have like 52 cards. So just 1 out of 52, there's only one ace of spades out of a whole deck of 52 cards. That's not very good chances, right? It's not half the deck, so you don't have 50-50 chances. It is possible. It could happen, so it's not 0, but this would definitely be unlikely. There's a better chance that you're going to draw another card, not the ace of spades, but you could definitely draw the ace of spades. That's a possibility. How about a coin landing on heads or tails? You'll notice here they're saying heads or tails. Either option is good. You can get heads or you can get tails. This is actually be certain, because you have to land heads or tails. They didn't tell us which one. If they just said find the coin landing on heads, then we'd say, oh, it's 50-50, because we only land heads half the time. But because they said heads or tails, this one's actually certain, because it's always going to land on heads or tails. There's only two sides on the coin. So this is because it's both work. Because it said or. And we'll get more into or probabilities later on, because actually a big part of probability is finding like, okay, I have more than one option that works. Here it was heads or tails, either one worked. And that kind of can change how you calculate the probability. So we'll get into that later in like section 7b. Okay, winning the lottery with one lottery ticket. So you went out, you bought one lottery ticket. What's the probability? Well, technically, yes, you could win, right? There's a chance, right? I think it's less than 1 in a billion. It's very unlikely. You're probably not going to win, but there is a slight chance. So we have to say unlikely, but I would almost be tempted to say impossible, because it's just so unlikely. You have better chances of getting struck by lightning twice in the same year than you do of like winning on a lottery ticket. So lottery tickets are really a waste of money, and I'll hammer that home this whole unit. If you don't get to the end of this unit and feel like, wow, why does anybody ever buy a lottery ticket? I'm not really doing my job, because they're a real complete waste of money. Because the chances are so slim. That's what we're going to get into here. So it's unlikely. It's almost impossible. Yeah, there are better and worse lotteries, and yeah, some people get lucky and do win. But if you go out and buy one lottery ticket, your chances you win are super slim. They're really low. Rolling a standard six-sided die and getting a 12, well, standard six-sided die is 1 through 6. So trying to get a 12 with a 1 through 6, is not going to happen. This is technically impossible. There is no option where you could actually get a 12. It's 1 through 6. So there's no 12 side. Now, if you had like a 20-sided die that has a 12, then you could do it. But we're doing a 6-sided die. It only has 1 through 6. It's impossible. This is 0% chance. Flipping a US quarter and not getting heads or tails. Yeah. I added this in here for some reason thinking I didn't have an impossible example, but I do have an impossible example. I don't know why I added it. I wanted a likely example, but I think I wrote it wrong. Oh well, that's my bad. Anyways, this one's also impossible, right? Because I'm not getting heads or tails. Well, we have to get heads or tails. We just said it's certain that it's going to be heads or tails, so the opposite option is going to be impossible. So yeah, it's definitely impossible to not get heads or tails. What are you going to get instead? The only options are heads or tails. So this would be impossible. All right. So most of the time we can kind of get an idea about whether something's like unlikely, likely, 50-50 chance, that kind of stuff. Most of the time. Sometimes it gets harder, and that's what we're going to get into later. We're trying to figure out is this impossible, likely, unlikely, 50-50 chance. But the big idea is it has to be one of these options. It has to be somewhere between 0 and 1. Anything from impossible to certain, that's the limit. It's always going to be fraction, decimal, percent, somewhere between 0 and 1. It can include 0 and 1. Okay. Now, when you do probabilities, there's actually several different ways you can do probabilities. The first method is to do what we call relative frequency or empirical probability. This is where you actually go out and you do an experiment, you make an observation, and you calculate the probability based on that. So you go out and you survey 70 people and find out what percentage of those people had health insurance, say. Then you find the likelihood that in that same group of people, they're like the big group, not just the 70, but the overall group, that a random person will have health insurance. You say 35% of your survey sample had health insurance. Now you can say, well, there's a 35% chance that you walk up to any of the people in this big group and they might have health insurance because I found that from my sample. Same thing can work for, do an experiment. Say you just sit there and you flip a coin over and over again. And you get 40 heads and you get 60 tails out of 100 flips. So then you can say that coin has a 40% chance of getting heads because you got 40 heads out of 100, 40%. Now we know that coins actually have 50-50, and so relative frequency can be a little different than the actual theoretical, and we'll get to theoretical more later. We'll spend more time with theoretical. But there's a good strong argument for using relative frequency because there's a lot of situations where you can't maybe calculate theoretical easily or at all. So relative frequency is still really commonly used because you can actually do it most of the time. You just have to go out and do your experiment, collect your observations. So it's based on the results, what we actually get doing an experiment or doing a survey. Subjective is kind of the, okay, we're not being really rigorous, really hard. We're not going out there and calculating numbers. Subjective is just I think this might be what happens. It's an estimate based on just your experience, intuition. You use this a lot. We actually use this all the time. But anytime you just say, okay, I think this is going to happen. And you didn't actually crunch numbers, you didn't actually do an experiment, but you just go, I expect this. Even though it hasn't happened yet, you kind of know what to expect. You kind of know how long your teacher's going to lecture for, or you kind of have an idea of how long it takes you to load the dishwasher. Stuff like that, you kind of have an idea. That's still a probability, though, because sometimes it takes longer, sometimes it takes less, and you're guessing how long it's going to take. So that's going to be subjective. We use this all the time. It's just an estimate based on past experience and intuition. It's not based on data. We're not collecting, information like the relative frequency. It's not based on what should happen. It's just what we expect to happen. Kind of our intuition. Theoretical. This is actually where we'll spend most of our time. This unit is with theoretical probability. Theoretical is what should happen. What we expect to happen based on the numbers. This is where you crunch in some numbers and figure out what should happen. To do theoretical, we're divide the number of ways an event can occur. So we're looking for positive results. If I'm trying to draw a card, I want a 3. I'm looking at how many 3s are in the deck of cards. That's the good options. That's the way events could occur over the number of possible outcomes. Well, I look at how many cards are in the deck of cards because everyone's different. That's the number of possible outcomes. So theoretical, it's divide. You're always going to divide to get this. And that's why you always end up with fractions. Number of ways the event can occur by the number of possible outcomes. Of course, number of possible outcomes is all the options. So that's the bigger number. It's going bottom. The small number is going to be the number, of ways we can get what we want. That's going to go on top, and that's why we always end up on a fraction that's going to be like less than 1, because we're not going to end up with a improper fraction or a fraction that's bigger on the top. We're not going to end up with that. We're always going to end up with either the top and bottom match, which will give us 1, or the top is smaller, which will give us something less than 1. Okay, so subjective probability. Let's talk a bit more about those. The subjective probability is the most common method for finding probability. You use this all the time. Whether or not you think about it, you actually do this all the time. Use it when you say, I think this gas station is going to be cheaper than that gas station. That's subjective probability. You're in your brain, you're just, okay, I kind of remember getting cheap gas here before. And so you're using your past experience. You predict which homework assignment will take the longest. Okay, well, I should do this homework first. It's going to go quick, and then I can start working on the longer assignment. That's a prediction. You don't always know. Sometimes what you think is going to be shorter might take longer, or vice versa. So you think about it. You kind of schedule, you plan. You're making a prediction every time you do that. You're kind of thinking, okay, I think this is what happened. People predict elections. Even without going out there and doing surveys and reading surveys and stuff, they'll say, okay, I think I know who's going to win based on, what I'm hearing, what I'm seeing. They look at their social media and they talk to their friends and they go, well, from what I'm hearing and seeing, I think this person's going to win. And that's a prediction. You're making a prediction. That's a probability. It's a likelihood. How likely do you think it's going to be to happen? So it's good to know the difference. When are you doing subjective probability versus when you're doing like relative frequency or theoretical probability? So let's determine that for a couple of these statements. So each one of these is a statement about probability. We're going to determine which kind it is. So the first one says, it is impossible for you to draw a joker from a deck of 52 playing cards. So a standard deck of 52 cards does not include jokers. If you include jokers, it would be more than 52 cards. So this is actually a statement. This is a theoretical probability. They actually went and they did the crunching. They said, okay, there's no jokers in that deck. It's impossible to draw a joker. That's not subjective. This is actually theoretical. They've done the math. They didn't tell us what the probability, I guess, except for telling us it's impossible, which is the same thing as saying it's 0. But that's theoretical. They're actually doing what should happen. Okay, I am 100% sure there will be snow at least once more before the spring term is over. So I'm doing this in the spring, so that's why it says spring. But if it's a fall term, then don't worry about it. But no matter what, I'm probably going to be right. There's going to be at least one more snowstorm before the semester is over. That usually is true for our climate in our area. So this one though is definitely subjective, right? I'm not basing this on data. I didn't go and calculate the data of like how many days of snow and not snow and all that kind of stuff. But in my past experience, I can say I usually expect to see at least one more snowstorm before the end of the semester. So this would be subjective. I'm not actually crunching the numbers. I'm not going out and collecting data, but I am kind of thinking, okay, what do I see? What's my past experience leading me to believe? I rolled that die plenty of times, and now I'm sure that 2 comes up more than 5. Well, the big thing here is that they rolled the die. They did the experiment. As soon as you start doing the experiment and trying things out, that is your relative frequency or empirical. Because this is where you actually perform the experiment. You're actually going there and say, okay, what did happen when I did this? This is what happens when you do a survey too. So again, when you go out and you collect survey data and you get a percentage, percentages could be probabilities because anything less than 1% like that is fine as a probability as well. Yeah, that's doing experiment, collecting observations. This is relative frequency. That what should happen. It's what did happen with your sample, with your experiment sample. I estimate you will get 20 heads when you flip that nickel 40 times. This is again going to be theoretical. We know that we should get about 50-50 on a coin flip. 50% of the time you get heads. So they say, well, out of 40 times, 50% would be 20. That's the number of times. So yeah, this would be a probability. They are trying to look at that and say, okay, yeah, because of theoretical probability, half the time you should get this. This is what they're doing. They're saying, yeah, half the time, 50%, 50-50, you're going to get heads out of that 40 flips. That's going to be about 20 heads. So be ready to think about the different options. We're going to spend most of our time in theoretical. You can see how subjective, it's important. We use it all the time, but it's kind of informed by our own logic and reasoning or past experience. Relative frequency, you can actually do the experiment and observations, but that means it can kind of vary from situation to situation. I can flip a coin 100 times to get one result, flip it another 100 times to get a different result. So that's going to vary. Theoretical is going to be the one where that's what it should be. We can calculate it and say this is what we expect because of the theoretical probability. Probably the most important one. It's one we'll spend most time on. But before we get to it, we do want to spend a little bit more time with relative frequency. Now, I was going to bring dice to do this today. I forgot to, so I'm going to probably just make up some numbers. But we're going to roll some dice and see our results for relative frequency. So with relative frequency, we collect data and then calculate the probability. Anytime we perform the experiment or collect survey data and calculate the percentage of a result, we are finding relative frequency probability. We calculate the relative frequency by doing this. First, we count the number of experimental trials, or observations. How many people did you survey? How many times did you run the experiment? That's the total. That's going to be your denominator. It's going to go on the bottom of the fraction. Then you count the number of successes. So whatever you're looking for. If I'm looking for people that did have health insurance on my survey, those are the successes because they did have it. Or the number of times I rolled a 5 when I rolled my 6-sided die. I'm looking for what result I'm looking for. That's my success. Success doesn't have to be a good thing. If you're a survey person who's looking at death statistics and you're looking at how many times this disease killed a person out of the times that people had it, then that would be your success would be death. And so be careful. Sometimes people see a word like success and they think, oh, it's got to be a positive thing. No, it's what you're looking for, the result you're looking for. And so it depends on what you're looking for. It could be a negative thing. I could be looking for, how often this disease killed someone. And then since that's what I'm looking for on my survey results, my data collect, that would be my success in that case. The probability of this disease killing someone, I could do that. So it really depends on what you're looking for. Okay, once you got that number of successes, that goes as your numerator goes on top. And so you just create this fraction, which you can of course turn into a decimal or percent. It doesn't have to stay a fraction from the data. So again, the probability of event A is going to be, event A results over the total number of results. And again, this is for theoretical, for relative frequency or empirical. So this is not theoretical. This is just for experiment ones. So you're looking for the number of results, from your experiment or your survey that are what you're looking for, success over the total number of results. So, this is the total number of experiments. How many times you did the survey, ask the survey questions, how many times you ran the experiment. Okay, so let's find the probability, relative frequency probability of rolling 3 odd numbers when rolling 3 die 5 times. So we're going to roll 3 die, we're going to roll them 5 times, and we're going to see what we get each time we roll them. And we're looking for 3 odds. Odds on each roll. I might actually roll some dice online instead of trying to just do this. Because I figure if I just make them up, I'll probably come with some really random, weird results. So let's roll some dice. I'm just going to use a computer program to roll some dice. Okay. Okay, I got Google to roll 3 dice for me. Okay, so first one I got, so the, 5 rolls, my first 5 rolls, I got 2, 3, and 1. And so I was looking for the odds, I didn't get it. So I'm going to try rolling again. And I got 4, 2, and 1. I got 1, 1, 4. So far, no joy. I'm not getting 3 odds, but that's kind of how it works. You never know what you're going to get. 5, 5, 4. I'm going to try one more roll. And I got 1, 2, 5. Okay, so With our experimental probability, we're saying how many successes we get. So we got, out of all these rolls, there was always at least one even in all these. So no success out of 5 rolls. This is 0 out of 5. We actually got 0%. So right now we're sitting there saying it's impossible to get, 3 odds. That's what we're saying because we didn't get it. This is how an experiment goes. You never know what's going to happen. You do the experiment, you see what results you get. But let's try another 5 rolls. So 5 more rolls. So we can expand our experiment. See if we get a little bit better results. Okay, first one I get is 5, 2, 1. And then I got 2, 3, 4. And then I got 1, 4, 5. I'm still not getting very lucky with these 3 odds. Let's try one more time. 2, 5, 3. And I guess one more time after that. 2, 5, 3. I got so close so many times, but never quite all odds. Nope. And not got a single time. So out of all these rolls, we never got all 3 odds. So our experimental in this case would be, I'm sitting here trying to roll it a few more times, see if I can get odds, but I can't. Okay, so this time I would actually get, still no success. And now it's actually out of 10 rolls, right? Because we did 10 rolls and we still didn't get it. Oh, here, finally got the roll of all 3 odds, but yeah, not in my first 10 tries. So it'd be 0 out of 10. I think I added 3 more, so eventually got to the point where I did 3 more rolls. I got 1 success out of my 13. That's what I eventually managed to get for my probability. If we got a couple more rolls. So this is experimental. It's all based on what happens. And it's not going to be what we expect. The theoretical probability, what we would expect to happen is 1 out of every 8 should be all 3 odds. We expected that often. But yeah, we didn't get it till our 13th roll. So experimental and in this relative frequency, and the theoretical, they don't always match up in real life. We'll talk later about how the more times you run your experiment, the closer you should get to theoretical. We'll get more into that later on in the unit. But for now, it's just important to note that relative frequency is what happened, and theoretical is what should happen, and they don't always line up, because there's a random chance. We don't always get what we expect. So sometimes you get something close, but not quite, and that's what we got here. And of course, we didn't even get close, really. We got 0%. That's not that close to the 12% we should have gotten. So yeah, either way, even after 10 rolls, we had 0. I think we got to 113, but 1 out of 13 is 7.7%. So that would be 7.7%. You just divide the top by the bottom and get the percentage and find out, that's not very close to the 12.5% they're expecting. But that's relative frequency. You actually perform the experiment, count the number of successes, divide by the total. That's relative frequency. Okay, let's get into our major last part of this, which is theoretical probabilities. That's going to be what we're going to spend all of our time on in 7B. Most of our time throughout this unit is going to be working on theoretical probabilities. We're looking at what should happen now. So when we say probability the coin lands on heads is 50%, we're thinking of the theory that the fair coin has equal chances for heads and tails. That's the theoretical method of probability. It's a theoretical way to think about probability. To calculate theoretical, we're going to count the number of total outcomes, total possible outcomes. That's going to be the bottom number. So all the different possible outcomes you could get. On top, for the numerator, we're going to put the numerator. I got a spelling mistake. Numerator, not numerator. Count the number of outcomes in the event that we're looking at. So we're looking at this event happening, trying to get all 3 odds was our event in the last part. That's what we're looking at. But here we're not doing an experiment. We're saying what should happen. The number of ways you could get 3 odds, like 111 or 113. Look at all those different possible options. That's kind of what's going on top. So the top number is going to be the number of outcomes that fall just within our event. And then we create a fraction from those, and you can of course turn it to a decimal percent, like we said before, and that's our probability. So a probability of an event occurring, we're doing the number of different outcomes for event A over the total number of outcomes. That's what we're doing. So for example, what was the probability that you roll a 4 if you roll a 6-sided die? Of course, there's 6 sides on a 6-sided die, so 1, 2, 3, 4, 5, 6. Those are 6 options. So I try to roll a 4 on a 6-sided die. There's only one option that works, right? There's only one 4. So there's probability of a 4. You know, that's what I'm looking for the probability of getting a 4. Let's say there's one good option. So there's one good option over the total number of outcomes. Well, on a 6-sided die, there's 6 outcomes, right? So there's a 1 out of 6. That is my probability. 1 out of 6, of course, you can turn that into a percent or decimal. So you can take 1 divided by 6 and see that you get 0.16 would be the decimal. Multiply that by 100, you get 16.7% if you round. So that's about 16.7%. That's rounded, so I'll put the little squiggly equals to say it's not exactly 16.7. That's why sometimes we'll leave it as a fraction because you get exact value. 1/6 is exact, 16.7 is rounded. So the 1/6 is just a little bit better number. If you're trying to tell someone what the probability is, it's better to be exact than be rounded. That's our chances. So it's always good options, the options you're looking for. You have options that fall into event A. There's only one outcome that is getting a 4 on the dice. Right? Out of the 6 sides, there's only one 4. There's only one good option of rolling a 4 at 6 sides. Let's try that. Let's do the theoretical probability. The 6-sided die will be an even number. So for evens, I'm looking at, I could have a 2, a 4, or a 6. So the probability of getting an even, well, now my good options, I've got 3 different results that are all good, right? So now I'm going to have 3 on top. Whoops. Yeah, 3 on top. But the total is still 6, right? Because there's still 6 total sides on the dice, so the bottom side's 6. Now be careful, don't leave as a 3/6, because that's not a simplified fraction. My math is going to be picky. I'm going to pick it on the test. You should simplify your fractions. If you're not super comfortable simplifying fractions, your T84, T30 calculators, they all simplify your fractions. If you have a T84, you just divide 3 by 6. Yeah, it gives you a decimal, but that first math button will let you turn stuff back into fractions. So you just say enter twice, and it turns it back into fraction, and it does simplify the fraction for you. Yes, 3/6 does simplify to 1/2. If you have the TI30 and you need to simplify fractions, it does it actually even easier. That's why I recommend it for the class, because I know it makes it easier for a lot of people. So, and to do my fractions, I would just take 3 divided by 6, and then well, if I did it that way, I'm going to have to press a different button than I meant. That's not what I meant to type. I meant to do the fraction button. So I meant to do 3 fraction 6. I just get so used to using division, and it will simplify it to 1/2. So use this fraction button, a little n over d, and now I'll turn it. Actually, if you do have a decimal, though, if you did 3 divided by 6 like I did, and you want to do it that way, there's this little f to d up here. So you just hit the second button, type that f to d, and then it's going to turn that decimal into a fraction. And so we get 1/2, and so you can get the same 1/2 either way. So there's a couple different ways to do it. But your calculator should simplify those fractions for you. If you type it in and then just make your calculator simplify it, that's good. So I'm going to expect simplified fractions. In this case, it would be 0.5 or 50%. 0.5 turns into 50%. That one's exact this time. My math lab will say which one they want. If they want a fraction versus a percent. On the test, I'm not going to be too picky unless I say, well, I want an exact answer or whether we're asking for a fraction. I'm probably going to want to avoid these percents unless, if they're rounded at all. If they're not rounded, that's probably okay. But if they're rounded, then it's better to stick with a fraction. A lot of times it'll take more work to get to the percent because we'll already have the fraction. So that's why I'm not too worried about it, because I don't know why you do the extra step of getting percent. You already have the fraction. The fraction's good enough. Okay, that's just basic probability. Again, basic probability is all about finding the number of good options over the total number of options. Let's do a couple more. That one was with a set of dice. Let's do with some of the set of cards. So we have a standard deck of 52 playing cards, and we're going to replace cards before we draw new cards. We're not going to worry about when we pull the card out, it's not in the deck anymore. It's getting it back in there. And we're going to find the theoretical probabilities for these 3 options. First one, drawing a 7. Now, if you're not comfortable with the deck of cards, it is down here for you. This is what a deck of cards looks like. I'll try not to do too much of deck of cards on the test, but they happen definitely on the homework quizzes. That's why I want to make sure I showed you what a deck of cards is. So deck of cards, 4 suits, hearts, diamonds, spades, clubs. Every suit has all the numbers, 2 through 10, and then jack, queen, king, and ace. So there's 13 cards in each suit. 2 through 10, there's 9 of them, plus the 4 face cards, that's 13. And so together, 4 sets of 13 makes 52 cards, or 52 cards in a deck of cards. So I asked for the probability of finding and drawing 7, so I would do probability of a 7, right, because I'm trying to get 7. Again, think about the number of good options. Well, there's a 7 of hearts, there's 7 of diamonds, 7 of spades, 7 of clubs. There's 4 sevens, so there are 4 good options, and there are 52 playing cards, so the total number of options are 52. When I draw one card from that deck, I'm pulling it, reaching in and grabbing one card and pulling it out. There are 52 different cards I could grab, and 4 of those cards are sevens. This does simplify. You can do it in your calculator, but I just know from doing this problem a million times, dealing with deck of cards and routine probability, that these both divide by 4, so you get 1 over 13. One card out of 13 a suit is 7, so that's why it's 1 out of 13, basically. 1/13 of all these cards are sevens. What about drawing a spade? Now spades, so if I'm drawing a spade now, there's a lot more than 4 spades, because it's not just the 4 cards. Spades is this whole set, which means it's actually 13 cards, right? We said there's 13 of each suit, so there are 13 spades. There's still 52 cards, right? Like we said, we're not keeping a 7 out, we're leaving it in there. So we'll deal with what happens when you draw more than one card later on. But today we'll just keep it simple. We'll just draw one card, and then we'll put them back and start over each time. So here we have 13 possible spades out of 52 cards. This one does simplify because 13 divided by 13 gives you 1, and 52 divided by 13 gives you 4. 1/4 of the cards are spades, which makes sense. 1 out of the 4 suits is spades. So 1/4 of all these cards are spades cards. That's where your probability is 1/4. There's a strong correlation between percentage and probability. The percentage of cards is pretty much the same thing as the probability of getting that card. Since 25% or 1/4 of the cards are spades, you have a 25% or 1/4 chance of getting a spade. Last one, drawing a jack of diamonds. There is only one jack of diamonds. So when I want to find the probability of getting a jack of diamonds, instead of writing that all, I'll just put that there because that's what I mean, jack of diamonds. There's only one jack of diamonds right there. That's the only one because he is a jack and he is diamond. All the other jacks are different suits, so it's only this one guy that works. Then there's only one good option, one jack of diamonds out of the 52 cards. And that would be our probability. There's a 1 in 52 chance that you're going to draw the jack of diamonds. You have a better chance of getting a jack, a better chance of getting a diamond. Try to get specifically the jack of diamonds. The only good option, that's pretty unlikely. There's only 1 in 52 chance. Okay. Now, most of the time when we find probabilities, we're not too worried about these simple just drawing one card or doing one coin. Most of the time we're going to do more things. You play a game of cards, you usually have a hand. You have 5, 6, 7 cards in your hand. You flip coins, you probably flip more than once. So most of the time we're going to deal with situations where the events include outcomes with multiple parts. They're flipping multiple coins, drawing multiple cards. So that's going to be typical. And what gets hard is counting the number of possible results. When you're only drawing one card out of a deck, that's not very many options. There's only 52. But since you draw 2 cards, now you've got combinations, these pairs, and it actually makes a lot more options. And as soon as you draw more and more cards, you get more and more possible outcomes. That's why 5-card stud, the typical classic poker game, is still kind of complicated. It's really complex because there's so many different possible hands of 5 cards. So there's lots of different options. Okay, so it can be really tiresome and it take a long time to list all the possible combinations. So let me show you kind of what happens if you try and start doing that. So we talked earlier about flipping 2 coins, and we only had 4 possible outcomes. We had heads, 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 tails, tails, heads, and tails, tails. There was only 4 possible results. Let's look at what happens as soon as you flip 3 coins. So first flip could be heads or tails. And then on the second flip, you had heads first time and got heads again, or you got heads and the tails, or again tails and heads, and then tails and tails. But then on the third flip, you also could have heads or tails. So you could end up with head, heads, heads, or you could end up with head, heads, tails, or heads, tails, heads, or heads, tails, tails, tails. And so by putting all 3 flips together, you end up with 8 possible outcomes. And this is just for flipping 3 coins. So I'm just flipping 3 coins. Coins only have 2 sides. This is a pretty small list, even though it's getting fairly long and getting complex to figure them all out. But this is all the options for flipping 3 coins. You do another coin, you end up with like 16 options. It gets even bigger. The more coins you add, the bigger those options get. You go to like Yahtzee, where you're playing with 5 6-sided dice. you have way more possible combinations because you're not just doing two, for each flip. You're doing like there's 6 sides of the die, and you're doing lots more than just 3, coins. You're doing like, 5 dice. So the more options you get, the bigger it gets. But there is a shortcut here. This is why we're going to mention the multiplication principle. The multiplication principle says that you can look at each part of the outcome, each step in the outcome, where you're flipping a coin, drawing a card, rolling a dice, whatever it is, and you can count the number of options there. So like for the first flip, there are 2 possible outcomes, heads or tails. Same thing for the second flip. Yes, I got it twice here because I could get heads and then heads, tails, or tails and then heads, tails, but each time I only have 2 options, right? Heads or tails, because I'm flipping just 1 coin. So I still have 2 possible options. I could get heads or tails. Third flip, well, it's the same coin, so I still have heads or tails, so I have 2 options. What you can do is you can actually multiply the number of options for each part, and it will give you the total number of possible options. 2 times 2 times 2 equals 8 possible outcomes. And this always works. So if I'm trying to count a big set, like, how many different cards I could get out of, drawing cards from a deck 5 times, I can use the same thing, this multiplication principle. Or if I'm trying to roll a die, so many times, or roll so many die, I can do this and kind of figure out how many possible options. You look at the options for each part, you multiply those all together, and you get the total number of possible outcomes for this. So this is a really common thing we do in probability. Because a lot of times we don't want to sit there and list all the options. You get much more than 10, 15 options, and it just gets a pain. And it's not hard to get much more than that in options. For example, what if you go to a bar and you're trying to look at the different combinations of food, so you can get a beer, there's 10 beers on tap, so you have 10 choices there. You can get an appetizer, there's 6 different appetizers you can pick from. There's 5 different desserts, and there's 4 main dishes at this bar. So if I want to figure out, like, okay, how many different possible meals, like combinations I could get, so like if someone picked one at random, I could start thinking about like what's the chances they pick this meal. I'd have to count all the different options. So I'd be like, okay, here's different beers with 6 different apps, with 5 different desserts, and 4 different main dishes. I have to combine that all, and it ends up being a pretty big number. But thankfully, because of the multiplication principle, that's the big thing. This multiplication principle lets us take each one of these options and just say, well, because you have 10 options here, 6 options here, 5 options there, 4 options there, so you can just multiply those together. I can do 10 times 6 times 5 times 4. I guess we use times that because we get the multiplication. That would give me the number of possible combinations. So you do 10 times minus times 6 times 5 times 4. And we get 1,200 possible options. So just out of these, there's 1,200 combinations, 1,200 different meals you order. This is why I think it was Baskin Robbins or whatever the ice cream place where they're like, hey, we have so many different options for ice cream. Well, it's because they had 3 scoops and then they had like 40 flavors. Well, by the time you have 40 choices for your first scoop and 40 choices for your second scoop and 40 choices for your third scoop, you end up with a huge number of options, because you can mix and match all those different flavors. And so that's kind of what they're doing. They're using this whole multiplication principle to figure out the number of different flavors there are. So this is what you do anytime you want to figure out all the different options. So now if I was going to go say, what's the probability if you get this one specific meal out of all the different options, it would be like 1 out of 1,200, because there's 1,200 different meals you can make if you pick a meal at random, if you use like a kind of random meal picker or something. Let's try another one. Say you flip a fair 2-sided coin, you draw 1 card from a standard deck of 52 cards, and you roll a 6-sided die. How many possible outcomes are there? Since you have to do all 3 steps, you have to do a 2-sided coin, which gives you 2 options. You draw 1 card from a standard deck of 52 cards, so I've got 52 choices for the cards. And you roll a fair 6-sided die, so I've got 6 sides for the die. We multiply those together to get the number of options. So I have 2 times 52 times 6, so 2 times 52 times 6, and I get 624 different options. That's just 1 coin, 1 die, drawing 1 card. As soon as you like get a second card, or you get a couple flips on your coin, or you get more rolls on your die, this can get so much bigger. So this is just a quick way to list it. Who wants to list all 624 options? Like heads, Queen of Hearts 1, heads, Queen of Hearts 2, heads, Queen of Hearts 3, and then you have to do the same thing with tails, and the same thing with all the other numbers. You can see that would be really long. It's 624 options. So the multiplication principle is a really cool tool we can use in probability to count these big lists quickly without actually having to sit there and list them all out and count all the options. We use the multiplication principle. We look at each part of our outcome, each step in the outcome, and then we multiply all those option counts together to get our total number of counts, our total number of outcomes. Okay, let's use the multiplication principle, calculate a couple more probabilities. We're almost done. After this page, we've got one more left and then we'll be done. So suppose 3 6-sided dice are rolled. What is probably all 3 dice will land on 5s? So we're rolling 3 6-sided dice. We want all 3 of them to be 5s. So we're probability of all 5s. Okay. Now, before I get too much into the multiplication principle, just want to point out, people get confused on this first part. How many good options we have? And I get a lot of people say, well, don't you have like 3 good options because you get 3 5s? No, we have 1 good option. Because the only good option is if all 3 dice land on 5s. So the only good option is 5 5 5. That's the only one that works because we want all 3 dice to be 5s. There's not multiple options here. It may be tempting because you said, oh yeah, let's use the multiplication principle. But for each option, there's only one good choice, 5. And you do 1 times 1 times 1, and you get 1. So for the good number of options, it's 1. There's only one good option. All 3 dice having to be 5s. That 5 5 5 is the only good option. Anything else? You change any of those numbers, so anything besides 5 doesn't work. Now that's the easy part though. The hard part is figuring out how many different options are there. We need the total number of options, and this is where we use the multiplication principle. Because we're rolling a 6-sided dice, we know that every time we roll it, we have 6 options. So the first die we roll, we have 6 options. The second die we roll, we still have 6 options. The third die we roll, we still have 6 options. Because here I'm looking at all the options. I'm not looking for just the good 5s. I'm looking for the total possible number of outcomes. So I multiply 6 times 6 times 6. And multiply that out. And we get 216 possible outcomes. So there are 216 combinations of just 3 dice. Well, 3 6-sided dice, there are 216 possible options. You can see how there'd be even more if you're doing Yahtzee, right? Like with 5 dice, it'd be way bigger. But you can use that multiplication principle. So now instead of sitting there and counting all the different options for rolling 3 dice, because who wants to do that, right? I don't want to list 260 possible options. How easy it would be to just miss one? Just be a pain in the butt. So instead, we say, okay, I'm rolling 3 dice. Each time I have 6 options. Multiply those together, and you got the total number of outcomes. So this includes 111, 112, 113, 114, and 211, and 311, and 411, and 511, and 526. So, it has all the options included in here because we use 6 by 6 by 6. I got 260 possible options. That's how powerful the multiplication principle is. It's a really strong rule, and it really works good for us to count these quickly and not have to do it by hand. Say you go to a restaurant and you're going to choose a meal at random. So you have some kind of random meal picker or something. You have 3 main dishes, 2 side salads, and 4 desserts. So these are the options. 3 main dishes, 2 side salads, and 4 desserts. You like all the main dishes and salads, but you're hoping to get your favorite dessert. What are the chances your meal will come with your favorite dessert? So we want to find the probability of our favorite dessert. Okay, so I do need to use the multiplication principle now to find the good options. Good options, we're going to say, the only one I really care about is the dessert, so I'm happy with any of the main dishes. I could get any one of the 3 main dishes, and it's still good, right? So I like all main dishes. Same thing with the side salads. I like both of the side salads, so either side salads could be good. So I have 2 options there that are still going to make me happy. But when it comes to dessert, you want to get your favorite dessert. We don't want any other dessert. We want just the favorite dessert. So we're going to multiply by 1 because there's only one good option for dessert. So there's actually only 6 meals where we would like it, where we got our favorite dessert, because we have, first main dish with the first side salad, or first main dish with the second side salad, second main dish, so on and so forth. And we end up with 6 different combinations that work, be good, but not, and as long because we also have our favorite dessert. So we have 6 good options, but for total, now we're counting everything. We're not just worried about our favorite. We have all 3 main dishes, both side salads, and now we have 4 desserts. So we multiply those, and I get 24. Now there's 24 total options. So 6 of the good options out of 24 total options. And if I simplify my fraction, divide both by 6, you get 1 out of 4. 1/4 of the options of the meals are going to make me happy because they're going to have my favorite dessert included. The other 3/4 are going to have some other dessert that I'm not as excited about. So again, multiplication rule, it works, and we can use it for both the top or the bottom. You don't have to just use it for the total. A lot of times that's what we use it for, because totals are usually the big part, so we want to use it. Sometimes use it for the top as well, and figure out that part. Okay, last one of these multiplication principles. You roll an 8-sided die and flip a coin. What are the chances you get an even number and tails? So I'm trying to find the probability of an even and tails. That's the combination I want, even and tails. Again, I want to think about the good options first. So if I'm looking at good options, well, my 8-sided die, my even numbers will be 2, 4, 6, and 8. Because I have 1 through 8. So 2, 4, 6, 8. I've got 4 good options. 2, 4, 6, and 8. I've got 4 good options for the 8-sided die because there's 4 evens. And for the coin, there's only one tail side, right? So there's only one tail side. So there's actually only 4 good options. So I could have 2 in tails, 4 in tails, 6 in tails, 8 in tails. Those are all good, 4 good options. You didn't have to use the multiplication principle here. You could just list all the options, right? You can see that it's 2 in tails, 4 in tails, 6 in tails, 8 in tails. 4 options, and that's it. You're done. Everything else has an odd or a heads. We only want these 4 are good. So that's the top number, and top number is always the good options of it. What you're looking for. This is the count of how many even tails there are. And then total, we're looking at all the options. Well, now I have an 8-sided die, so I rolled that. I have 8 total options, right? And 1 through 8 is 8 options. And you flip a coin, you have 2 options because there's heads or tails. So actually, there's 16 total options for doing this. Between 1 in tails, 1 in heads, 2 in tails, 2 in heads, so on and so forth. You have 16 possible combinations. So 4 out of 16 is our probability, because there's 4 good options out of the 16 total. When you simplify that fraction, we get 1 out of 4. Again, I got 1/4 again. Pick the one that has 1/4 for an answer. So that's what you really need to be ready to do. We're going to do a lot of this. We're going to make it a little more complicated when we get to 7b, is finding probabilities, because we're going to add more components to it. We're going to say like multiple options. You might have doing this multiple step stuff like that. So we'll have to worry about that later on. But that's the basic idea. To find probability, you got to count the number of good options over the number total. And I want 2 more little sections. You're not going to see a lot of homework on these, but they're good things to know, especially as we get further in. You'll see them pop up, so I want to just kind of give you a heads up on these. First one is probability of an event not occurring. So either an event occurs or does not. That sounds silly, but that's the 2 options. What that tells us, though, the probability of the event combined with the probability of the event not occurring is all your possible outcomes, and that would actually be 100%. So the probability of something happening plus the probability of it doesn't happen, combine that, you get 100% of the options. So it's 100% of the probability. So we can actually find the probability of it by actually finding the probability that it doesn't happen and subtracting that from 100%. So if you know that a basketball player has a 60% chance of making his free throw, well, then you also know that he has a 40% chance of not making it. Let's say 60% are away from 100%. That's his probability of not making it. If you know that 1 out of 4 guesses on your multiple choice is going to be correct, you also know that 3 out of 4, because 1 or 100% minus 1/4 is going to be 3/4. 3/4 would be the chance of not getting it. So this probability of not happening is important, because a lot of times it might be easier to find the probability of something not happening than it is of finding a probability of happening. So let's do it for this example. So I have the probability of rolling a number larger than 2 on an 8-sided die. But instead of just counting the number of options bigger than 2, let's actually do it the opposite way. Let's find the probability of rolling 2 or less, and then subtract that from 100%. So, for example, probability of 2 or less, well, that's easy, right? Because there's only 2, 1 and 2. Because 1 and 2 are the only ones that are 2 or less. So there's a probability of 2 out of, and it's an 8-sided die, so there's 8 sides. So it's 2 out of 8. That's probability of 2 or less. So if we do 1 minus the probability of 2 or less, we'll actually get a probability of more than 2, or larger than 2. And so that's what we can do. We can take 1 and subtract, 1 again is the same thing as 100%. Subtract probability of getting 2 or less, and we'll get the probability of being more than 2. So in this case, well, 2/8, you subtract that from 1, you get 6/8 is what's left. Because there's 8/8 total. Subtract 2 of them, you're left with 6 of them. So 6/8 is a probability of getting more than 2, because we did 1 minus 2/8 equals 6/8. So you can do it with fractions, you do it with percents, right? You know, if they told us what percent was, I don't know, was 2/8 divided by 8 is 25%? Yeah, 25%. So this would be like 100% minus 25% equals 75%. So you can do it with percents, you can do it with fractions. The idea is there are times where it might be harder to do the probability straight on. Instead of trying to find the probability of this thing, we might find the probability of not that thing and subtract it from 1. And that's a pretty common technique in probability. There are times where it's just easier to go backwards a little bit. The other last thing I want to talk about here is odds. We're not going to see a lot with odds, but it's something important to note. Odds are very similar to probability. You might even think of it as the same thing. It's not quite, though. It's a little bit different. So when we say probability or the chances, 1/2 of flipping heads, we're saying, you know, it's 50%. We're saying that 1 out of every 2 flips is going to be heads. However, when we use the word odds, when we look at odds, we mean something different. We mean we're comparing the number of favorable outcomes to the number of unfavorable. So odds is different. Odds compares favorable to unfavorable. So when instead of saying there's a 50% chance, if you're saying odds, you'd say the odds of flipping heads are 1 to 1. There's 1 good side, heads, to 1 bad side, odds. And that's actually, if you go look up the lottery, they don't publish the chances, the probability, they actually publish the odds. And the odds are showing the number of good outcomes versus the unfavorable outcomes. And it sounds silly, but it actually makes the probability look a little bit better than it is, especially for someone that doesn't understand probability. If I say 1 in 10 versus I say 1 in 11, 1 in 10 sounds better until I tell you that the 1 to 10 is, you know, odds and the 1 to 11 is probability, and they're actually the same, you know, because they're just different ways of looking at, you know, probability. You know, probability versus odds are a little different. So you know, the lottery, they like to do that. They like to use the odds because it looks better, but it's not. So what are the odds of drawing a queen? So the odds of drawing a queen from the standard deck of the cards. So the odds of a queen, you know, I'm not going to use that probability notation because this is finding the odds of getting a queen. That's going to be, well, there's 4 queens, right? Odds of queen, there's 4 queens, and out of the 52 cards, but I'm not doing probability, so I'm going to say, okay, well, there's 48 cards. Yeah, subtract 4 out of the 52, there's 48 that are not queens. So it's 4 to 48. It's actually the same as, you know, 4 out of 52 probability. These are the same thing. This is just writing it a different way. There's 4 good queens to 48 non-queens. There's 4 good queens out of 52 cards. They mean the same thing, but you can see how this looks like, oh, that's better chances. 4 out of 48 is better than 4 out of 52. No, it's not, because this is 4 good to 48 bad. This is 4 good to 52 total. So the 52 actually includes the 4 up here. That's why it looks a little different. If I want to do the odds of getting the Queen of Hearts, the odds of the Queen of Hearts, do a little shortcut there. Well, then I'm saying there's only 1 Queen of Hearts to the 51 cards. I have to pull out the 1 queen. I'm doing odds, not probability. Let's switch here. That is the same as 1 Queen of Hearts out of 52 cards, you know, for my probability. So 1 to 51 is the same as 1 out of 52 probability. The odds, 1 to 51, is the same as probability, 1 out of 52. So again, odds are a little different. I'm not going to worry too much about odds. You won't see it, you know, on the test or anything. But it's just something that's important to know so that you understand when you see odds come up some way, that they are slightly different than probability. Okay, that's it for today. I am done. We'll let you go, and I'll see you in the next one.